Welcome everybody to week 2, day 4 of game development. I'm going to start today by going over a little bit of the theory of lighting, because we've been talking about this a little bit. And I've been sort of talking about normal maps as a way of like adding detail to a surface, but we'll go through some of the actual theory of like what a normal is. I talked a little bit about it yesterday, but we'll do more today. Let's see, get this thing out of the way here. There we go. All right, so pull that over there and there. Okay. All right, cool. So, what does it mean to be normal? I don't know if you guys can answer that. There's actually two different meanings to the word normal when you're dealing with math and game development, and I repeat myself because game development really is math underneath the hood. If any of you guys have been sitting in on my IS50B lectures, like yesterday I was asking them if they remembered how like two lines intersected and like where to detect where a line intersects and things like that. Everyone's like, it's 8th grade math, man. I didn't know I'd have to use that. Game development really is just math under the hood. And so what normal means, there's two things. If I'm talking about a normalized vector, a vector is usually when you're in a 3D game, a vector is an x, y, and z. Usually, there's sometimes a fourth element in there called w, or sometimes it's RGB, red, green, blue, and then sometimes there's a fourth one called alpha on top of that. But if we're talking about a normalized vector, that means that it has a length 1. And normalized vectors are used extensively in the math behind video games. If you have magnitude on a vector, then it breaks a lot of the calculations we do. So we normalize them all first to have a length of 1, and then we do our stuff on it. So just to make it confusing, a normalized vector is completely different from a normal vector. A normal vector is if you're thinking of like a plane, like a piece of paper, there's no paper around here. Interesting. Can I get a piece of paper? No, don't worry about it. I'll use my hand. So if you have a piece of paper, a plane, the normal vector is the vector sticking out from it. So if you have something on like the XY plane, like this, the normal vector is sticking up in the Z direction. Does that kind of make sense? So it's flat in the X and Y direction, like horizontal. So a plane normal to the XY plane, the horizontal floor basically is the XY plane. A normal vector is sticking straight up. So a normal vector sticks out from a surface. And we use this for a lot of different purposes. If you throw a ball at a wall, then the ball reflects around the normal vector. So if you if the normal vector is this and the ball comes in like this, it reflects out like that. Whenever you do collisions and bouncing and things like that, things reflect around the normal vector. And for light, so whenever we light a surface, the normal vector chooses the direction that light bounces in. And so when we have a normal map, that assigns a different normal vector to every point on the surface. So if we didn't have a normal map, it would just be flat. It would just be a flat sheet of paper. So even though it looks like a rocky mountainside, it's just flat. And all the light bounces off it the same way. And what it looks like to our human eyes is that it's a wallpaper that somebody took a picture of a rock and just wallpapered it on a flat wall, and it looks really bad. And that's how video games used to look, right? Like, it takes extra time and effort to, do a normal map. And so back in the day, this is what, things looked like, right? It looked flat, and there's just a texture of a brick wall on the sides. And, you can see like these aren't real rocks, they're just flat pictures of rocks. And we just dealt with it because that was, how does the meme go? I'm limited by the technology of my time, Stark's father. Daggerfall, by the way, is actually my favorite Elder Scrolls game. And it's really weird because the graphics are terrible. You're talking about a game that came out when I was in college 20 something years ago. It's really this is Daggerfall Unity. So people have remade Daggerfall using the Unity engine, and it looks better. Still doesn't look great. Looks better, you know. That's not possibly Daggerfall. That's probably from Elder Scrolls Online or something like that. So yeah, the original Daggerfall looks like this, you know, and and so they didn't have normal maps. Everything just looked flat. Like somebody just took a picture and just pasted it on a flat surface. And so with a normal map, every point on the wall can have a different normal. In other words, the engine will consider the angle of the wall to be different at every point on the wall. And that allows us to do things like have bricks that act like bricks that actually come out from the wall a little bit, or at least they look to. Okay. Todd Howard graphics, yeah. Honestly, Daggerfall has the worst graphics of any of the Elder Scrolls games. I guess Arena is technically an Elder Scrolls game, but it's barely. Daggerfall is definitely the worst graphics, and I wish they would make like a 64-bit remake of just Daggerfall. That's kind of what the Daggerfall Unity people are doing. They open sourced it, by the way. So back in the 90s, like companies were a lot more favorable towards open sourcing their engines and things like that. So after they finished Daggerfall, they gave out the source code to everybody. So that was cool. Quake, they gave out the source code to it. Nowadays, companies are like, no, it is my precious, you know, and they don't share source code anymore. But I do wish somebody would actually remake it. Daggerfall Unity is a nice step in that direction. But the graphics are still terrible, and the gameplay, it's still really awkward gameplay and stuff like that. So I'm hoping they make like a really nice looking version of Daggerfall, because it really was the best Elder Scrolls game. Okay, so yeah, we don't need to know about that yet. Yeah, let's talk about lighting. So how much light, like I've got my hand here, right? And there's a light right here. There's also a light up here. So how much light my hand gets is based on if my normal vector is pointing straight at the light, it's fully lit, right? Just based on the distance. The closer it is to the light, it's brighter. The further away, it's a little dimmer. But if I start tilting my hand, you notice how my hand starts getting shadowed. That's because it's picking up less and less irritance from the light bulb. Okay, so the amount of lighting you get on a point is based on how close the normal vector is towards the light. And it's basically, I don't have the equation in here somewhere, but yeah, it's basically a cosine. Yeah, if the angle is 0, then it's fully lit, to 90 degrees, not lit. So, so there's kind of 4 different points of lighting, four different ways of lighting. There's ambient lighting. Global illumination kind of falls into this a little bit as well. Ambient lighting is just a light that's just in the room. It doesn't come from any light source, and we typically do this when it would be black, right? Like I'm in a room now, and if I were to turn off the light in front of me and the light above me, the only light coming in would be from a window that has shutters drawn. And so if I had the sun outside doing directional lighting, the shutters would technically block the sun. They're sort of opaque, pretty much. And so there's a couple gaps in the shutters. Here, let me show you guys what this looks like. Right there. So you see there's a couple gaps where like maybe a few lines of light would come in. But what would happen is that back here you would just see a couple lines of light from the sun, and then the rest of the room would be pitch black. And that's not very accurate. In daytime, even if I turned off these lights here, Ada, can you turn off the overhead light? Ada, flip the switch here. Even if I turn that off, there's still light in the room, right? Just because light comes in through cracks in the walls.
Also because of the lamp.
And because of the lamp here. You want to turn that one off too? There's a little knob right there. Yeah, just twist it to the right. No, other way. Okay. Yeah. See, there's still light in here, right? And so you know, when you have a situation like that, if you try doing it accurately, what happens is that this whole room would be pitch black, except for, you know, there's the shutter. There'd be like that one little gap in the bottom there. It'd throw one little light down there, one little line of light down there, and the rest of the room would be absolutely black because there is no other light sources right now except for the sun. And yet, as you look around, you can see I can read in here just fine. Ada can read her book, even though, and that's because light bounces around, right? If you're using a ray traced engine, there's something called global illumination that actually calculates that. So when light comes in through a window, then it does this thing where the lights bounce around, and they'll sort of add a general illuminance to the room, and so the room will be brighter or darker. And if you pull up the blinds, the whole room will light up. It's actually really cool. But in a normal game engine, non-ray traced game engine like this, you can turn the lights back on. Thanks. Then oftentimes you have to simulate that. You simulate that using something called ambient lighting. So ambient lighting just adds a little bit of light to, and this one too, B, if you don't mind. Thanks. Thank you, girl. Thank you. You're a good helper. It's grumbling at me. That's it. Thank you. You got to earn your cheeseburgers. Child labor. So we use ambient lighting to sort of simulate that, right? Where we just turn a knob up a little bit, and there's just a little bit of light everywhere you go. And that's also because it's absolutely not fun to be playing in a pitch black video game. If you can't see anything you're doing, there's a disconnect. Like I'm moving my mouse, I don't know how fast I'm turning. Right? In real life, in a pitch black room, I can close my eyes and be like, all right, I'm turning 90 degrees. Turning 90 degrees, I'm walking 3 steps forward. In a video game, it disconnects your experience from the mouse or game controller because you can't see what's happening. And so it's very rare for a video game to just be like, it's black. And you got to play the game not seeing anything. That's Doom 3 did it, and it was widely criticized for how dark the game was. Has anyone here played Doom? Not Doom 3. Yeah, what, Doom? Maybe this Doom, was it 2008? 2000, jeez, which one? I don't know. Not Doomsday. Which one was it with like the flashlight? Yeah, and so the levels were basically pitch black. And you had a flashlight, because you're a space marine. You can't use your flashlight and gun at the same time. Because in real life, people don't put their flashlight on the gun. That just doesn't happen. And so the whole level's black, and you're getting attacked by monsters. And so if you want to, and so you swing your flashlight around, you're like, oh, there's the monster. It just teleported in behind me, because they did that a lot too, which was, in my opinion, a really bad game design. You'd go through, you'd clear a room, and then you'd walk out, and then a monster would teleport in behind you. And that sort of defeats one of the guiding principles of a first-person shooter, which is you're supposed to kind of have area control or like area understanding. And so like if you clear a room, and you should be able to put your back to it, right? And then look into the next room. And they would just drop things behind you as a jump scare, basically. But they did it over and over again. It was super annoying. And then when the monster teleported behind you, you swing around, and you shine your flashlight, and you go, oh, there it is. But then in order to shoot it, you have to put your flashlight away. And then it's pitch black. And the only light you can see is from your gun. So you have to fire your gun to flash, lights. You're using your bullets as flashlights, essentially. And then, of course, you run out of ammo. It was just a very badly designed game, in my opinion. And so one of the most popular mods for it was to make the flashlight not stupid. And so that game really would have benefited from some ambient. I mean, that was the whole point of the game. Like, the point of the game was they wanted to be like all dark and spooky and jump scare you, monsters coming out of closets, that kind of thing. But the actual implementation was just not fun. It was just not a fun game. And it was a really, really annoying game, actually. So having a little bit of ambient lighting in there where you could at least see what was going on a little bit, like where the walls are and stuff, would have helped a lot. Okay, so directional lighting is this. So that's sunlight, basically. So you can think of like an infinitely far away light source, and so all the light comes down at the same angle. When you adjust the rotation of the sun in Unreal Engine, when you click on the sun and you rotate it, that's actually rotating the angle of the light from the directional light. And there's usually one directional light in Unreal Engine. It supports up to 2. And so if you have like 2 suns, or if you have a sun and a moon in the sky at once, the engine handles two directional lights, And you might be able to add more than that, but some of the systems just won't, like volumetric lighting will not accept more than 2-direction lights. It's just an engine limitation. Because, there's the sun and the moon, and, there you go. So, there's also point lights, and so we've seen point lights before in the engine. When you drag the little light bulb thing over, it shoots light out in all directions. Okay? And these typically have like a maximum radius that they can light up. That's because lights are actually very expensive in a video game. So, especially when you're doing realistic shadowing. So every light, like I have three lights in the room right now, right? I've got this one in front of me, the one above me, and the sunlight. So that's 3 sets of shadows that it has to compute. So if you look behind me, where's the thing right there, you can see there is a shadow being cast by the overhead lights. The overhead lights are kind of back at an angle. And so it's casting, where's my finger? There it is. It's casting one light there. You can see there's another shadow because there's 2 overhead lights actually. And so it's actually casting 2 shadows. And then they're illuminated a little bit from the lamp in front of me and from the sun. And so for every object in your room, for every light, you have to cast a shadow. And so that can become very, very expensive, And if you have players running around shooting guns, creating lights, that creates a new light, and light moves. Moving lights are even more expensive because a shadow like that can be pre-computed. That filing cabinet back there in a video game is probably not going to move. It's probably going to be set as static. Static means it can't move. And the lights are also, they're probably not static, they're probably stationary. Static means they don't change at all. Stationary means they don't move. And so what's the difference? Well, you can turn them on and off, right? And so since I can turn the light on and off, it's going to be set to stationary, not static. And so what the game engine will do is it'll actually very accurately compute. Let's get this mirror image, so it's hard for me. Whatever. That whole shadow back there, there. That whole shadow back there, it can all be pre-computed. And so that's what's happening when saying lighting needs to be and you hit build lighting only. What it's doing is that it's pre-computing the shadows, because how long that thing takes. And we're doing it on low quality, and we're doing it on a tiny level, and it still takes a while, right? And so you don't want to have to do that in real time. You don't want to have to do that when you're running your game. And so dynamic lights, like a player who's running around on fire, as they're emanating light, they've got to do all of those shadowing calculations in real time. And if you've got a lot of people on fire running around, then your frame rate will go like that. So it's very important in a game. Static lights don't really matter because they're always there. And so the game engine will just, when you do build lighting, it'll just pre-compute where all the shadows are, and it just basically bakes that into a texture and pastes it on the wall. It's something called a light map. And so that shadow back there would be pre-computed. And if it's a stationary, which means it could turn on and off, it'll have one for the lights on and one for the lights off. And then when you turn the light on, it just switches out the light map. Okay. Do you guys understand that? So you got to be careful with your lights. Static lights don't matter as much. Dynamic lights that can move around, that can really affect you. Like if you've got 10 rockets and each rocket emits light, and especially if you don't attenuate their light, that's what I was kind of talking about here. The point lights are attenuated, they have a little radius, and outside of that, they don't affect anything. And that's to cut down on the amount of computations you have to do. Like if I were to take a flashlight, and have you guys ever done this, like where you make a little bunny, and you do this thing, with Ada you do snail, stuff like that. Have you guys ever done that, like shadow puppets and things like that with your hands? So think about what's happening there, because video games will do that. You can do that in a video game, a modern engine. You can do that. You get a light source. You hold up an object, like the little Stonehenge-looking thing I put up on the hill yesterday. It casts a shadow on the ground, right? But if it's dynamic, then as this little bunny ears things moves around here, the flashlight that I'm holding up to it, it has to compute the outline of the thing. It computes the outline of the bunny ears, and then it has to project it into a volume back towards the wall, and it gets bigger, right? Because it's a point light. Point lights, the shadows will get bigger as it goes out. And so it creates a 3D volume based on the outline of the bunny. It extrudes it out, getting bigger infinitely, and everything that it hits gets shadowed. And it's doing that every frame. And that's one light source and one object. When you've got 1,000 objects and 7 lights, then that starts really tanking your frame rate, because you've got all these objects moving around. For every object, for every light, it has to compute the outline, project a shadow volume over the world, find everything that it intersects in the world, and then add darkness to those objects. Every frame of the game. Okay. So that's something you guys got to be careful of. Static lights, okay, no big deal. Dynamic lights that move, problem. Okay, so spotlight is I don't know if I've shown you the inner cone and outer cone, but they actually have this in Unreal Engine. I think that by default, when you put a spotlight into Unreal Engine, it's just a single cone. But there's actually an inner cone that you can set, so you can have an area that's bright, and then a dim light, and then nothing, right? So that's a fairly common thing you do anytime you have a light, like the recessed lighting back here, would actually probably be simulated as a spotlight, because it's the bulbs in a recess in the ceiling, and so the light only comes out like this. It doesn't go out sideways because the ceiling's blocking it. It's recessed lighting. Okay. So yeah, that's the math I'm not going to talk about right now for this, but I wanted to show you guys like normal maps and roughness and things like that. So a specular reflection is like the shiny spots like you see on my forehead because it's hot here and I've been sweating. So you can see there's like shiny spots on my cheek too. That's called a specular highlight. Okay, it's where the light reflects off smoothly. Like if you look at a pool ball, this is what pool ball 3D specular. Yeah, sure. This is how we used to do a lot of these things in 3D because they're easy. They're plastic also, which is nice. Yeah. So anytime you see like a pool ball, they're very shiny, right? So you can see these specular highlights on them here. Do you guys know what I'm talking about? These like little white, areas here. These specular highlights here. Does that make sense to you guys? These little white dots there. You guys with me? Specular. Okay. So specular highlights are stronger on a smooth surface, and that's why when we do Unreal Engine, we control the specularity, and that controls the highlight strength, and then the roughness. And so a rough surface will do what's called a diffuse reflection. As light comes in, if it has a rough surface, light will scatter this way and that way and the other way. On a smooth surface, they all reflect off like a mirror. Like a mirror is perfectly smooth, right? Not perfect, but you know what I mean. And so a rough surface will tend to not have any specular highlights on it. Like when you shine, like if you look at the carpet down here, like you see how there's like no shiny bits on it. It's just it's lit. It's just there's no like shiny glowy things. Like maybe if it's like in shrink wrap or something, like if somebody put down plastic over it, then you'd see specular highlights on it. But it would look weird to us, right? If the carpet is shiny, you're just like, what's going on with that shiny carpet? Because the human brain like is really good at deciphering visual stuff, and so like, is the filing cabinet here, is this shiny? Is it smooth or is it rough? What do you guys think? You're getting it, you're just not an art guy. It's fine. You don't have to be an art guy. I'm not an art guy either. You just have to know enough to make a good video game. You know what I mean? What do you guys think? So Shammy says smooth. Anyone want to go with rough on this one? Any takers? Shammy's going with rough too. I usually think that you get at least a small team who can do specific things. Yeah, Yeah. Like, you don't want me doing art for your game. You know what I mean? However, as a programmer, you have to know enough about the art to get by. You know what I mean? Like, if you don't understand how lighting works, if you don't understand how highlights work, it doesn't matter how good the artist gives you. You're probably going to make a mistake along the way somewhere, and it's going to look terrible. You know, you just have to know enough to get by, and that's kind of the level that I'm trying to get you guys up to on this. It's just like having a passing familiarity with the math really underneath it, the physics underneath it, to kind of get by. Yeah. So yeah, it is smooth, and you can tell it because it's actually reflecting the shadow. You see that right here? There's the shadow is all mirrored. The shadow I'll use my mouse. The shadow that's coming down this way, you can actually see the reflection in it this way. So you can tell, like, without you guys ever having to come down to the mountains and touch a filing cabinet, you can tell it's smooth. And the human eye is really good at picking up clues like that. And if your carpet is fully reflective, you're just gonna be like, huh? And unless that's like a clue, like you're on an alien planet now, or aliens have switched out your carpet with metal carpet or something, it'll just be very jarring to people, and they will not want to play your game. If the art is if it runs contrary to what your brain expects, your brain tends to reject it. There's actually this really interesting theory called the uncanny valley. Has anyone jelly carpet? Yeah, I wonder what jelly carpet would. Let's see if that turns up anything. Yeah. Okay, that's pretty cool. Ada, you want this for your birthday?
What's that?
It's jellyfish rug carpet.
No, thank you.
No, thank you.
You already got me something.
I already got you something. That is true.
It is cool though.
It is. Yeah, it is cool. Yeah. Now, if I walked in and I saw that in a video game, I don't know. Like,
did you do a good job?
I don't know. Like it's definitely catching the eye. You know, I definitely like have a moment where I'd stop and look at it and be like, what does this tell me about the person that that owns this place? You know, uncarpet. What the heck did I just type? Uncanny valley. That's why you can't. Well, at least I can't type and talk at the same time. Yeah. So there's this notion called the uncanny valley, which is like humans. The human brain rejects things that are like supposed to look realistic, but there's something wrong with them. So like, here's like a robot. Ada, what do you think of that robot? Is it cute or is it creepy? Weird. Yeah.
Oh, that look at what that person sent you.
Yeah, the RTX on.
I mean,
Mario.
It kind of looks like an actual person. It's just that it looks weird.
Yeah, it's Yeah, that one. It's so disturbing. So, yeah. Unless that's something you're deliberately going for, the more realistic something gets, it'll kind of look cute. But then when it gets like kind of pretty real, but then like not there's something off with it, then the human goes like, and maybe it's because, I don't know, we're like, it's dead or something, or it's a zombie, some people have hypothesized that it's why Neanderthals went extinct, because Neanderthals look kind of like humans, but they're off somehow, and so humans are like, murder them, and then there's no Neanderthals anymore. Although some people have Neanderthal DNA, so there was some inbreeding, I guess, but. Stuffed animals are cute. Prosthetic hands and corpses are a little creepy. It's that's from the Final Fantasy movie, I think. Did you guys know they made a Final Fantasy movie? Ew.
What is that? What is that?
I have no idea. I've never seen that before in my life. Ooh. Wow.
We're talking to you. We're really talking to you.
He closed a production company called Edge.
That person's talking to you.
It looks like E.T. Yeah. Mars needs moms.
That. You're not gonna make me eat it now, are you?
To raise their own kids.
Are you sure this is gonna work? Whoa!
Why does Mars need some money?
I don't know. Oh, it looks so bad. Oh my gosh, that is just terrible.
What is that?
I don't know. It just looks terrible. It's amazing. Okay. Yeah, so the point here is that, like, when you're making a video game, as a programmer, you have to at least be aware of these things. You don't have to be an artist. And typically in a game company, you're not going to be an artist. You're going to be hired, if you're a programmer like me, you're going to be hired to be a programmer. You know? Or if you're a game designer, you're going to be hired to be a game designer. But you need to understand the technical limitations of the system. For example, every graphics card can draw a certain number of triangles per second. And so if it can draw 1 million, it's way higher than that. It's like in the billions, but I just want to make the math easy. If your video card can draw 1 million triangles per second, which is like state of the art for the early 90s, then if you want to get 60 frames a second, then you can only draw 16,000 triangles per frame. So every video games are broken down into frames. It draws the screen, then it draws the screen again, and it draws the screen again. If you do that 60 times a second, that's a 60 frames per second game, and that's what people shoot for. People shoot for 60 FPS. And so if your graphics card can do 1 million per second, then you're limited to 16,000 per frame. And so that's something called your triangle budget. So if you're a game designer, you have to understand that. Because you might be like, I want to put 1,000 monsters on the screen. Cool. You've got 16 triangles per monster. And so the technical limitations will shape your game design, right? Like maybe 1,000 on the screen is too many. Maybe we'll do 100 instead. Okay, well, your budget's 160 now, assuming there's literally nothing else on the screen. Is that enough? And the artists are gonna be like, I don't know, dude. 160 triangles is pretty sketchy. And so there's the sort of interplay between the game designers, the programmers, the artists, and the programmers oftentimes have to implement things for the artists because the artists want, like, I want hair that flows, and the programmer's like, yeah, we don't really have that right now, so could you put a helmet on them instead? Could you give them a hat so that we don't have to do hair? If you don't want to have to animate eyes, give them sunglasses. Depends on your budget. Depends on whether you're a AAA company or not, right? Like in games like The Last of Us, they will sit there and add huge amounts of realism and fidelity to the game. And when you're a small indie studio, it's just like, yeah, no, we're not going to animate people's faces. And we are not going to have many triangles on the screen. We're going to go with a low poly, thing. Unreal Engine 5, all the triangles tech has evolved. Yeah. Well, Unreal Engine 5, even still, like it streams a certain number of triangles onto the screen, and so you have to understand, like, how many you don't get free triangles, And so if your art looks terrible on a 3060 is kind of average these days, maybe a 2060 is average these days. If it looks terrible on a 3060, then you got to go back to the drawing board, and your artists don't like that. your artists really don't like having to remake stuff. You can use as many triangles as you want, yeah, but you can't, like, there's still a budget. You know what I mean? And so, like, if you put 1,000 monsters on the screen, all of them are going to degrade in quality to the point where they're just like these blurry messes, right? So, what? They didn't lie. It's just what Unreal Engine 5's purpose is that you don't have to do what's called level of detail. Yeah, and so in Valheim, it's like, is it worth any animation budget to, like, animate people's faces? No, it's not. They have 6 people on their team. I know they're hiring more, but there's 6 people on the team, and there's no dialogue really. There's a raven that talks to you, but the raven, like, communicates telepathically with you, so it doesn't even, like, move its mouth. Blah 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 blah. Nope, it's just a dialogue box that pops open to give you hints. There's absolutely no reason they need to animate any of that stuff. You know, and you can sit there and you can count the number of triangles in the shield, right? You see that? That's going to be one triangle. That's going to be one triangle. You know what I mean? So now I don't get it. So the notion is, I should probably explain level of detail. Remind me of that, and I'll talk about it after I get through this talk on lighting. But like, can you guys see that? How like this shield here, it's not round. You know, it looks like you know, like you can count how many edges the thing has, right? You guys see that? So this is a low poly game. It's a low polygon count game, and again, it makes your art budget easy to do. But everything ties together with each other. You know, like you can't. You know, you can count the pixels. Look at this. Look at that high quality texture on the boat there, right? On the left side here, you can literally count the pixels on the boat texture, and the boat texture is this really kind of garbage looking low quality timber thing here. So yeah, and you can look at the pixels here on the guy's helmet, you know, and they say that's a deliberate choice they made. They're going for a certain look. They wanted to have low quality, like their art direction was this. It was low quality art with high quality shaders. And so the shaders, like you can see how beautiful the lighting is here. You got some blue back here. You got some clouds. The water actually looks really nice. And so the Valheim deliberately chosen look was to combine really garbage models and textures with really, really nicely programmed shaders. Like look at this, like beautiful colors, you know. Like I've got a lot of screenshots of the game of just, you know, me sailing around, you know.
Do you want to show your students actually the game that we
Start with low poly. I can show them the game, I guess. Yeah. Yeah. So you can see, you can look, like you can see the pixels here. Like it's really bad, you know, but then it's got this really nice shading and weather effects and stuff like that.
I think they're focusing more on the nature. I think that's their whole point, to make it you can see the pixels on stuff that they don't really that more like building and focus more on the nature.
Yeah, so people have released high resolution texture packs, and they look kind of weird.
Like what?
It's almost disconcerting.
That's Valheim.
That is not Valheim. Why is it? Okay, it's not giving me Valheim. Anyhow, it's actually kind of jarring. Like I was actually originally intending to do like a high res mod for it.
But I'm saying no because the bricks just look. In some of the pictures, the bricks just look like you put like a giant paper, printed out paper on top of the actual stone of bricks, like that.
Yeah. Yeah. And I guess it's not too bad. Anyway. So,
no, it's pretty bad.
Gonna focus on programming first before you learn 3D modeling. Yeah. Yeah, like I said, if you wanna be a game programmer, like you can't just be like ignorant. You know, like you have to have an appreciation of like what the art budget is, like a triangle budget. You have to appreciate like how your shaders that you write are going to affect the art of the artists and things like that. So, okay. So the old way, anyhow, of doing it was you would create the old school materials would have a color, a specular, and a diffuse.
Do you know where my cup of water is?
Your cup of water is back here. So the old way that you do materials, like back in the 90s, is there were three parameters. There was base color, there was specular, and there was roughness. You can kind of think of it as that way. And nowadays, we have something called PBR. Have you guys ever heard of PBR before? A fun game is better than a good-looking game. Yeah, but like I said, if there's something about the graphics that are off, like that game that I showed before I started recording, it gave me serious Warcraft 3 vibes or World of Warcraft vibes, and I was just like, nah, I'm good. I don't want to play a game with that art direction, you know. Has anyone heard of PBR before? Walker has, yeah. No? Okay. So PBR is the new way of doing rendering. It stands for Pabst Blue Ribbon. If you ever been to the Clovis Rodeo, there's the professional bull riders. Right? I wonder what we're gonna get if we search for PBR. Yeah, so we got rodeo, Pabst Blue Ribbon. Where's the physically based rendering? Look at that guy. There we go. So we had to scroll down a while to find the PBR. So PBR means that rather than the old way where you just set a color, a specular, and a diffuse, which all these surfaces here have textures, the base color, specular, and diffuse. Now you can do things like have Fresnel, like the ability for light to bend as it moves through an object. You can have things like clear coat we talked about before. You can have you basically tell the game engine the physical properties of the material, and then the game engine will render it in a more realistic fashion. I guess that's the best way of
I can't tell
explaining.
which one's more realistic.
The one on the right's more realistic.
I know, but like the one that looks less realistic doesn't look exactly less realistic.
It doesn't look bad. Yeah, it definitely does not look bad. But like on the right hand side here, you can see that these things, like look at the difference between the knobs, right? See the difference there? And then the scope, obviously, the scope's the biggest difference here. And then they've added a little bit of texturing, normal mapping probably to that too.
It's getting cold.
It's getting cold?
Maybe it's because I was drinking ice water.
Okay. So, so the three things you'd set are the base color, the spec, and the diffuse. And this is the old way of doing it. The new way, diffuse, specs. Okay. Yeah, that's what it looked like. The teapot, dude. I don't know why, but like the teapot was just like the go-to like model we used for rendering things. And so we created here a black teapot with like a green speck and diffuse on it, and it just looks terrible. Look at how alias that thing is. Do you guys see how like jaggedy do you see how jaggedy the edges are there? Is that coming through on the stream? I can't tell because I'm on my local machine. Do you guys see how like jagged the outline is of the teapot? Right there. Yeah. So that's something called aliasing. And that's because if you're drawing a line, what pixel it lands on will kind of go in a stair-step pattern, and so it'll create these really noticeable lines. And like I said last time, the human eye is very noticed. Like there's a chunk of the visual cortex that is for edge detection, and so when you have sharp edges like that, it just kind of leaps out at you and it looks bad. And so modern games engines have something called anti-aliasing, where it will sort of blend these jaggedy stair-step edges together and make it look a little bit nicer. So this is the old way of doing a material. So you can increase the specular power, which makes it more specky, like more shiny looking, right? So this is a low spec power, higher spec power. This looks like a smooth, shiny plastic surface. This looks like a rough surface. So PBR is the new way, physically based rendering. And so what you do is you set things like, do you want clear coat? Yes or no. Is it metallic? Yes or no. Base color, spec, and then you can apply a normal map to it. So every pixel on the surface, every point on the surface has a different normal, so it reflects light in different directions if you want it to. It can have an emissive map, so every point on the surface can glow or not glow, like the Kmart sign that one of you guys was doing. You can have refraction, so you can have light bend through it. You can have an opacity map, which means parts of it can be transparent, some can be translucent, some can be opaque. You can do subsurface scattering. Subsurface scattering is like one of the biggest advances in 3D rendering technology, honestly, and it makes things look so much more realistic. The notion of subsurface scattering is that light doesn't just reflect off your skin. Light will actually enter your skin. If you've ever held up a flashlight to your hand, and you see the red glowing through it, light will go through your flesh, right? And if you try simulating human skin just by reflecting things off, it looks like it's made of plastic. And so subsurface scattering has both surface reflection and photons entering your skin, bouncing around a little bit, and then coming out. And that applies not just to skin, but to things like jade. There's a marble sculpture up there that, if this was my place, I'd hold it up to the light, and you could see the light bouncing around inside of it. Really, really important thing. The guy who developed that actually gave a talk at my college. He was applying to be a professor there. And one of the things that was fun about being in grad schools, we'd be invited to attend these lectures, and for prospective professors, and we would vote, we like this guy. This guy's a good lecturer, or this guy's terrible. And he gave a really good talk. I don't know if he got hired there or not, but it was a really interesting talk, and he talked about how to simulate it and stuff like that. So so emissiveness is glowy, so you can have an emissive map on it. And so if you put fog in it, you'll see the light kind of accumulate around it in the fog. There's all sorts. Do I have PBR? Yeah. Let me show you what subsurface scattering looks like. You guys see that? How light will kind of go through your skin. So on the left, subsurface scattering is off. On the right, it's on. Can you guys see the difference in the quality between this? No? On the left here, it looks very kind of plasticky. It's the exact same model, just with subsurface scattering turned on. Take a look at the chin down here. Do you see the difference? The chin? Because the light's coming down from this direction, so the light's going to bounce around through the skin here. Yeah, the eyes are noticeably different. Plus around the ears. One big thing is the nose. So with subsurface scattering off, the nose holes usually turn into these black holes, and they actually look really bad. You end up getting these black areas here that just look very unnatural. Because in real life, our noses are actually very thin flaps of skin, so actually quite a bit of light actually goes through them. And so with subsurface scattering on, the area inside of the nose will be lit a little bit. You can see here, it's black. Here, it's it's got that reddish glow from light coming through the skin. And so one of the tricks that we would commonly do is, put lights up people's noses. So if you had a character on screen and they're talking, that's turned up a little bit too high. Looks like the guy's made of Jello or something. Hey, look at this.
What the?
They turned it up way too high. But you can see how there's light on the inside of the nostrils there. So to simulate that, they would put lights up people's noses. And yeah, for marble and things like that too, you want subsurface scattering on. Jade.
Maybe they didn't make it actually Jello. Okay.
So so one of the tricks would be to put a light up somebody's nose. And edge highlighting is a very common thing in a lot of video games, where if you're trying to let people see something, if you put a very subtle edge around an object, then the human eye will pick it out better. So if you're playing some first-person shooters do this. I think maybe Borderlands does this. Borderlands. Do you guys know what I'm talking about? How they like draw a little like outline around it? Do you see this? Like, there's like a black line around the characters. That helps you pick out a character from the background. You see that? How like they have this this black edge going all around them on every character. So it is for their art style, but it's also so that so you can see things, right? Let's see if we can get a screenshot. Let's see if they're doing it here. Gulag winner. Yeah, I don't know. Yeah, but some first-person shooters they'll do a very subtle outline around something, so that you can see something like, oh, that's something. Because when you get shot, you can't. You're like, I can't see where it's coming from. It's really frustrating. And so video games will kind of help you out a little bit by, it's sometimes very subtle, but they'll put a little edge around it, and then your eyes like, oh, they're there. They're hiding behind the bush. Valorant does the same thing. Let's take a look at Valorant. I don't know. It's a really, I can't, look at the JPEG on that. I don't know. I can't tell Shammy. Sorry. But yeah, it's a trick that a lot of companies will use. That looks like comic books actually. Okay. All right. Yeah. So that would be like an example of like an edge highlight, things like that. There's all sorts of things, and one of the sad things about this class is that the game development industry is so huge that you can't even talk about all the things there are, you know. So I'm just going to go through these really fast, so at least you know what the term is. Okay, so pre-calculated lighting was what I talked about earlier. Light maps, where like that shadow behind me on the wall there, you can actually pre-compute what's lit, what's shadowed. You don't have to do it in real time. Very common trick. Anytime you have static lighting and static objects, it's very common to pre-compute all the shadows you can. Because in video games, you want maximum speed. You want all the frames you can get. Anti-aliasing, I talked about that with the teapot, right? So if you have a jaggedy edge, the game will try to smooth out the edges. And there's a lot of techniques on anti-aliasing. There's a lot. And there's temporal anti-aliasing, and so normal anti-aliasing means in a single frame it finds jaggedies and it kind of smooths out the edges. Temporal anti-aliasing looks for jaggedies that appear between frames. So like if you're walking towards a staircase and the staircase is really narrow, you'll get like this weird banding effect. And so it's like as you walk forward, you'll get these like moire patterns. You guys know what I'm talking about? Like if you're walking forwards, you get these weird patterns appearing, especially when you're at kind of a flat angle to it. And so temporal anti-aliasing will try to average out between frames, and so you don't see these weird kind of effects have you guys ever seen these in a video game before? Where like you're at kind of a shallow angle and the things start forming these like weird banding effects and things like that. Like this kind of stuff, a moire pattern. Have you guys seen this before? Yeah, like that. Yeah, it's a perfect example of it. That's a moire pattern. And so what you have is you have a bunch of stripes, and as you walk forward, it sometimes picks out the white one, it sometimes picks out the black one, but you're at an angle, so it's not even which one is which. And this just looks weird, right? Like if you're in a video game, you're seeing that, you're just like, what's going on here, you know? And so yeah, checkerboard patterns, especially when the angle gets really flat, it just starts looking like garbage. And so temporal anti-aliasing tries to sort of even out between frames. Bloom. Do you guys know what bloom is? Have you guys seen bloom? Shahab. Yeah, it's a good example of it. And it's very noticeable to the human eye. So do you guys know bloom? AKA the J.J. Abrams of video games. It's when you have like a street light and it does a glow. Yeah, that's a good one. So you have a sun here. It kind of adds almost like a lens flare effect to it. And it can be too high sometimes. Like yesterday in class, I had the bloom turned up really high, and you saw it just it can overwhelm you. But it's kind of that notion of like when you're going down the street and you see street lights and there's kind of that glow around it, like that. You guys see that? Or this? You guys know what I'm talking about? That little kind of light glow around stuff. Like an overexposure. Yeah, and yeah, especially when you're looking at the sun, it's like like in real life, it's like, oh, it's too bright. But like at nighttime, it's kind of the effect of like atmospheric haze around it and stuff like that. Light will bounce off in different directions. If you turn on volumetric fog, you'll get kind of a similar effect to it. So that's bloom, and sometimes bloom, like they added it to Oblivion, I think, and sometimes it just doesn't look very good. Yeah, so you see how like how there's like bloom coming off the shield here, off his armor, off this, off all the rocks. And yeah, like Simmons says, it does feel like overexposed. You're just like, it's so bright. Tone it down, dude. Come on. Todd Howard Bloom. Yeah, it's like, ooh, that's nice. Too much bloom. Yeah. Yeah, you see bloom everywhere. It's jarring, right? It just feels like you got cataracts or something. So it can definitely be done wrong. Now there's also something called HDR eye adaptation, which is completely different from HDR as you're normally used to talking about it. So this is one of those cases where people use the same acronym, high definition, whatever, in two completely different ways. So you guys all know what HDR is on like a TV, right? Do you guys know what? I should ask that. Do you guys know what HDR is on a TV? Like, there's like HDR 10 and HDR 10 plus. Have you guys seen this before on TVs and stuff? It's so funny. Like whenever they do comparisons of like images of like this is a TV without HDR, this is a TV with HDR. It's like they've been using the same set of comparison images since like the 1980s, like these sorts of things. Like they take one side and they wash it out, and then they just have the other side be normal. Because if your monitor is not HDR10, it can't render it, right? You can't actually see what HDR10 plus looks like on your monitor unless it's HDR10 plus. And so what they always do is they just wash out the old side. And I swear that these same like sample photos have been used. Like, all right, this is what a 720p television looks like versus a NTSC signal, and You always do the same thing. You just take one half and you just wash it out. And I swear, every like you could probably find, oh man, like monitors from the 1990s that just conventional HDR10. They just watch like the exact same things they've been doing for 30 years. Same photos. This is the old way. This is the new way. Anyhow, HDR10 on a TV, hard disk recorder. Yeah, that too. So HDR eye adaptation is for when your eyes adjust. HDR on a TV is having more pixels per color. So your typical monitor, like my monitor here, has 8 pixels for red. Did I say pixels? 8 bits per pixel. So for red, there's 8 bits that control how much red it has. 0, 0, 0, 0, 0, 0, black. 1, 1, 1, 1, pure red, right? Half, it's 50% red. And so 8 bits is 256 colors. So there's 256 shades of red available, 256 shades of green, 256 shades of blue. Combine them together, you get 16 million colors, which is pretty decent. But it's not all of the colors the human eye can see. So with HDR, HDR10 has 10 bits per pixel. So you've got 10 bits of red, 10 bits of green, 10 bits of blue. Ideally, sometimes they will cheap out and not do the full 10. But what that does, you're like, oh, it's only 2 more bits. Yeah, but every bit adds twice as many possibilities as before. So with 10 bits instead of 8, you have 1,024 shades of red. You have 4 times as many shades of red. You got 4 times as many shades of green, 4 times as many shades of blue. That is HDR on a TV, which is completely different from this. So HDR helps a lot with color banding. If you ever see like a dark scene, you'll see color banding like that. Yeah, like right here, like at sunset, because there's only so many bits for red, and when they start getting really dark, there's only like maybe 10 different shades of red in the lower regions of red. So when you have 8-bit color, you tend to get color banding, and then they'll do things like dithering, where they kind of like move, like the TV will detect where there's a band. It'll kind of dither, which means it moves some of the pixels up and down a little bit. But if it does that, then it's going to slow down the rendering of your screen. Some of these test images, you'll see bands appear on them and stuff like that. And so if you're playing a video game, you typically have game mode on to reduce input lag. And then you'll see color banding and things like that, more obviously. So when you have HDR, you get 4 times as many colors, so the color bands are harder to see. Okay, still there, just a little harder. So HDR eye adaptation is when you go from a dark area to a sunny environment, as Alex says. The first game to implement that is called Half-Life 2 Lost Coast. And I was at E3 that year when it came out, and I was talking to Robin Walker, who was the guy who invented Team Fortress. So kind of my personal hero, you know. I was like, oh, it's Robin Walker. Holy smokes, dude, you were my favorite, you know. And he was a nice guy. I talked to him for a good 20 minutes, and I was like, tell me about this Lost Coast thing. Is it a new game? He's like, is it a new Half-Life game? He's like, nah, it's just a tech demo, really. And so they did Lost Coast to sort of demo this HDR eye adaptation thing. So there's areas in it where you go into like a tunnel, and it might be better with the video.
What?
And so let's see. It's gonna be right here. Kind of weird they've never come out with Half-Life 3, huh? Let's see, where is the tunnel? There we go. Okay. So you're in a tunnel. So here you are. You're outdoors. You walk in, and everything kind of goes dark. And then when you walk out, you see how overexposed everything is? So the game is constantly sort of paying attention to how much overall light your eyes are seeing, because your irises take a little bit of time to get used to being in dark and being in light. And so when you walk from a dark environment to a light environment like that, break.
There will be a Combine soldier with his back turned. He is
Okay.
not there. So the
All right.
stairs where we made it to the
And
top
you see
of the
it.
cliff.
See how it
path
adjusts
to-
back there.
We'll head up the.
So
But we will kill him eventually.
you walk in, it gets dark, and then
Head
it
up the
overexposes,
stairs
and then
where
when you
we
walk
made it to
out,
the top of the
then your
cliff
eyes
path
adapt.
to
I mean, that sometimes
the
happens in
remains.
real life.
Yeah, yeah, they're trying to simulate your iris in games.
Is that
And
good or bad?
it's kind of
Okay.
annoying because like people don't like being blinded when they walk out a front door, you know. And so I've seen it used in some games, but I think in most they make it really fast. Like you walk out and your eye almost instantaneously adjusts to it because people really don't like being blind. In real life, your eyes actually don't adapt that fast. You know, if you're in a dark environment and you walk outside, you're like, you know.
People like playing video games because it's like a life where like it doesn't have the problems you have in life. Like you're like
Yeah.
I keep walking, I walk outdoors and then everything is so blind light. But when I'm indoors and I'm playing a video game and I walk outside of my video game house, I don't do that. But if you add that in, everybody's like, wow.
Yeah, imagine you're playing Animal Crossing, and every time you walk outside, the screen's just pure white for like 10 seconds. You'd just be like, I don't like this game. But it's realistic. I don't like this game.
No, that doesn't happen. You have to wait. They put up a loading screen and then you can start playing.
Yeah, the loading screen is when your eye is adapting to the outside. Very good. So yeah, you use that sparingly, I would say. It is in Unreal Engine. They do have a eye adaptation feature inside of Unreal Engine. Lens flares kind of combined with blooms, but yeah, you can add a lens flare effect to stuff. You want to go full J.J. Abrams. Two-sided lighting is when light goes through something. Like if you hold up a sheet of paper to a light, the light will come through it. You know, normally an object will just stop light, but something like a leaf, if you shine light on a leaf, you see the green light coming through the other side. So for really thin objects, you can enable two-sided lighting. And so it lights both the front and the back side of it. And you typically do that, again, with leaves and paper and things like that. Really thin things that light can go through. Self-shadowing, that's... there's a whole bunch of different technologies that have SS at the end of it, like full screen, HBAO, and things like that. Yeah, SSAO, that's one I was thinking of. Screen space ambient occlusion. And so, no screenshots of it, thank you. So with self-shadowing on, you can see there's light here, and this is one mesh, this lion head here. And so what's happening normally is that it just gets lit, right? Every bit of the statue gets lit by the lights. But what's happening here is that the nose of the lion is casting a shadow from the light. You got light over here somewhere on itself, so it's self-shadowing. And there's a lot of techniques. The HBAO. There's a whole bunch of different ambient occlusion techniques. Yeah, AO off, whatever. I don't know what MHBAO is. That's way too pixelated to see anything. Let's see if there's a higher. Let's see if there's a higher resolution. Nope. No, there's not. Yeah. You can see over here that the steps are getting more self-shadowing on them, but this is way too low resolution to see anything. Yeah, I can't make out. I can't make out anything on that. Battlefield. No, Rise of the Tomb Raider. Okay, so screen space ambient occlusion here, HBAO here, VXAO, whatever the hell that is here, and so you can see like all of these things involve something casting a shadow on themselves. And there's a bunch of different techniques for it. Some look better than others. I typically turn it off because it tends to look bad, honestly. Like the quality of shadows, especially on somebody's face, like from the nose, you'll get like these zebra stripes on the nose, and it's very disconcerting. Like it doesn't look good. Let's see if there's any other. Yeah, Witcher had it. Let's see if we can zoom in on someone's face. Yeah, that doesn't look too bad, I guess. Yeah, what I found with The Witcher with ambient occlusion on, like you get these weird, like the shadows would be in lines like this, and it just looked really, really bad. Yeah, so that's self-shadowing, ambient occlusion, SAO, HBO, that kind of stuff. In the background of this lecture, the people I'm staying with are trying to save a baby cat. Oh.
What?
It's also expensive. Are you talking about the frame rate cost?
Wait, what baby cat?
I don't know. I guess they got a baby cat. Yeah, exactly. It does have a frame rate cost, and to me, it's like if it's going to create artifacts that look terrible, just turn it off. So let's turn it off. Yeah, translucency, light beams. I showed you guys light beams yesterday. We're gonna have what are called God rays coming down. So titled because the like if you ever go to a church and they have like the service bulletin. Yeah, like this kind of stuff, right? Like it's very common in churches. They have like these God rays coming down. That's why they're named that, right? Because they're typically used on like service bulletins from in churches and things like that. Yeah, there's some more. Like there's the classic thing is like there's a cloud and then there's like a beam of light coming out of the cloud. Let's see. Yeah. Okay. So. The more correct name for it is called light shafts. And so that's pretty bad. You are right. The Thief series actually does darkness really well. Yeah, there you go. Yeah, that's the classic like church service bulletin cover. Well, like yeah, if you turn on volumetric lighting, and there's an option for turning on light shafts. That we talked about yesterday, and so you can get light shafts for free, or not free, but you don't have to code them. That's good. A lot of biblical, yeah, burning bush, yeah. I don't mean that in a disrespectful fashion. It's just like that's the association people have with like a cloud parting and a beam of light coming down. You know, that's the symbolic meaning, right? That we have associated with it. Okay, and then finally, I was going to talk to you guys about Mipmaps and LOD, right? So Mipmaps and LOD is how you handle, and this ties into Unreal Engine 5 because they're not using this anymore. And so that's the very exciting thing that Unreal Engine 5 is doing. They're telling you don't have to worry about this kind of stuff anymore because they're annoying. They're annoying to do right. So have you guys ever played a video game where you're walking forward and you see something just like pop into existence? Like maybe off in the distance, you're walking forward and like a house goes bloop, and there's a house there. You're like, huh? And you step back, bloop, the house vanishes. Bloop, house is back. Or like a tree all of a sudden grows branches, or like fences appear, that kind of stuff. Minecraft does it. GTA 5, yeah. Yesterday with the terrain, I don't know if I showed you guys, but by default the foliage only, like the shadows yesterday, remember I was getting closer and further away and the shadows would boop and they would appear. It's annoying. It's really annoying, and I like that's why I said I turned the shadows off rather than have that jarring sort of pop on it. And the foliage also by default only goes out 100 meters, and which is fine if you're on a flat field, but if you're on any sort of hillside, what you'll see is the other hillside over there be completely barren of vegetation. You walk forward and the vegetation just sort of appears in front of you as you're walking forward, and it looks really, really bad. So that's why I set the culling distance up to 50,000 centimeters, so that as like it'll progressively cull things, and so further away they're going to be less dense, but it's not really noticeable. As you walk closer, like individual flowers will kind of appear in the gaps, but it saves your frame rate while still not making it look like there's just this sharp line of flowers that are just kind of appearing as you head forward. So, why do these things exist? What is a mipmap? What is a level of detail? So, as you get, this is a great example. So, a mipmap is your full resolution texture here for some brick. What a mipmap is that they'll hold a lower res version of it, and a lower res version of it, and a lower res version of it, and a lower res, and a lower res, and a lower res, so that when you have a brick wall off in the distance, it's not actually drawing all of these pixels. It doesn't need to. If it's really far away, it's going to draw that brown pixel there, right? And then as you get closer, it switches in higher and higher res textures. And in order to avoid popping, it typically does filtering between the different mipmap levels, so you don't really notice the pop. If they don't do filtering, you'll see all of a sudden you'll just see that the texture get clear. So without mipmaps, with mipmaps, I don't see any difference between the two of them.
What is with that cozy cottage?
I don't know, it's just a cozy cottage. Yeah, I don't really see any differences. Maybe this is a little more blurred, I guess. Yeah. So when things get further away, it uses a lower resolution texture, and when it's done right, you can't see it. Oh my gosh.
What is that? What is that?
It's a mipmap. So this is the high res version, medium, low, and so.
Why did he put her face there?
And so when you get close to it, it'll use this one. You get further away, it uses that one, and that frees up texture memory. Every graphics card has a certain amount of video RAM on it, and so you can, in theory, use less video RAM if you have mipmaps. And also, because they're kind of blurred at low resolution, you don't get these weird moire patterns as well, as it's downsampling the high res version. And so you get these weird moire patterns. With bitmapping, it kind of blurs it out, so it doesn't look as bad also. So, yep, that's a mipmap. And it's basically for things off in the distance, right? So this is default, same texture all the way back. Bitmaps and anisotropic filtering is for when you're at a very shallow angle. It does extra filtering on it to make it look not terrible. Like when you're really close to the ground, that's when anisotropic filtering comes in. Show that to you. And so if you've played any video games on a PC, you've probably seen a setting for like anisotropic 2 times, 8 times, 16 times, things like that. And so what it does, it filters the things way out there at a shallow angle so that it looks better. Do you see, with that normal trilinear filtering, it's just sort of this blurred mess. With anisotropic, it doesn't look bad. It's for things at a shallow angle, and it does a pretty good job. It does have a cost though, so.
Have you noticed the lines in them?
No anisotropic filtering. It looks garbage, and here 16 times. It's still garbage over here, but it's better.
It's okay.
It's okay, yeah. No. So yeah, that's what anisotropic filtering is used for. Then LOD is the same idea as that, except for if it zooms out what's in the back by default, why do you get those weird moire patterns without mipmaps? Because what's happening is if all you have is the high resolution image and you go away, then what it's going to do, it's going to pick every other pixel, probably. And as you go further away, it's going to pick like every third pixel. But if it doesn't divide evenly, it's going to pick every second, then every third, then every second, then every third. So you're going to get more white, more black, more white, more black, and it starts forming these moire patterns. And so when you blur it, it has the side effect maybe of hiding those moire patterns, especially if it's at an angle. And so if you have mipmap set up, the blurring on it will help to a certain degree with that. So level of detail is the same notion except for models. So if you have a 3D model, what about taking the averages of nearby pixels? Yeah, now you're starting to talk about filtering, right? So like, so when you start averaging together nearby pixels and things like that, that's a filter, right? So with no filtering on, you get the moire patterns. If you start, there's bilinear filtering and trilinear filtering and anisotropic filtering, and then there's temporal anti-aliasing. There's a lot of different filters that we put onto our video games to hide those really jarring jaggedy effects. And sometimes people actually just don't use anti-aliasing if you're running it at 4K, right? So at 4K, like the pixels are small enough, like you don't actually see the jaggies. But like this is what anti-aliasing is. So anti-aliasing kind of is a filter, right? So it blurs. It's a blur basically, where it finds an edge and blurs it. And there's there's all sorts of different kinds of anti-aliasing and different costs. Yeah, so this is what you're talking about, like averaging the nearby pixels. So like the quincux is this pattern, and so and they have different costs and different performance benefits and things like that. So you can kind of look at the different things, or you can just play at 4K resolution, 8K, downscale it. All right, so level of detail. So level of detail is, there we go. I hope this is interesting for you guys because there's a lot to game development. I'm just kind of going through the big topics right now. So level of detail is when you have multiple, level of development. No, not level of development, level of detail. 3D games. So that's pretty dramatic. So level of detail is when you have different versions of the same model for up close, further away, and further away. And so you can see this is 60,000 triangles or polygons, 6,660. So Ada, take a look at this. Mm. Which one do you think's the best?
I know you're trying to get me to see the leftmost
The
one,
leftmost
but it also
one.
depends which one you're going for.
True.
Because I mean maybe like probably nobody would want that, but like if you're like doing like a pixelated game like this, you would probably want that one in style. That's
actually a good answer, girl. Like if you're doing like a Valheim game with low things, like that might be part of your art style.
No, there's like a typing game that has, sort of has like those details, like crumpled paper.
Yeah.
But also this one, it has, I guess, more of a stone look. This one looks like metal. This one has more of like actually carved in
That's
wood.
true. That's a really good answer, girl. Yeah, your art direction will actually control some of that. Like if you're Valheim, they're like, we don't want things to look like this because it's going to be jarring. Because if you have the one super high res model in a game where everything else has the count the triangles look to it, it's going to be jarring, right? But there are tools that will generate levels of detail for you automatically. The trouble is that a lot of times they don't work very well.
Okay, maybe that's in a video or like, guess the picture. Guess what's behind this really triangle.
So let's say that you're looking at this thing off in the distance and you walk forward. If the silhouette of this thing doesn't match the silhouette of this in every angle, which is really hard to do because you've lost 90% of your triangles, right? Like you can look at this thing from every angle, and as you walk forward, this is going to pop into existence. That's the nose, right? And that maybe you can hide if it's really far away. But when the silhouette, when the profile changes from every angle, you have to make sure it's exactly the same, and like an arm pops in or something like that, it is jarring. It is really annoying. Yeah. And so what the Unreal Engine 5 thing is they're like this. Just make the high-res version, and we will handle the level of detail for you automatically. That's the whole point to Unreal Engine 5. As you get closer, you will see more triangles. As you get further away, it will smoothly draw less triangles. And it will just figure out how many triangles to draw based on how close it is to the screen. So you have a triangle budget, and it can also dynamically probably reduce the triangle count of everything evenly to kind of degrade the quality across the board. But the notion is you don't have to go through this process of making LODs, and then you have to go through the process of testing them and walking at them and walking away from them and seeing if there's a noticeable pop, right? Like if you had a tree branch sticking out here and the low-res version doesn't have it, when you walk forward, a tree branch is just going to go boing, like that, and you're going to be like, you know? For something like this, you probably wouldn't be able to tell, right? Because, yeah, sure, this tire is pretty angular here, but like if you're seeing that like across a football field, there's not going to be enough detail on the screen to see it. And as you get closer, it draws a rounder wheel, and as you get closer, it draws a rounder wheel. So yeah, 35 polygons, 500, 3000, you know. So again, you know, from far, far away, you probably could tell. That would probably pop because there's no barrel on the whatever that's called, the drum magazine. So, yeah. So that's a little detail. You guys understand? So it's the same model, just different numbers of triangles in it. And so the game engine will typically have a distance and be like, all right, we'll see this one up until 5 meters. We'll see this one from like 5 to 15 meters. This one 15 to 30 meters. This one 30 to 60. This one 60 to 100. This one 100 plus. You guys understand? Like, so like you set kind of like the range, and then they'll sometimes blend between the two also. Are there game software that makes shapes of things other than triangles? Yeah, triangles are sort of the default, but polygons, triangle, strip. Okay, this could be risky. Safe search is on. Okay, good. All right, so yeah, so there's different ways you can construct meshes. Polygons, triangle fans, quads, tri-strips. There's a pool, vertex pool method. Let me show you this. So when you use a triangle strip like this, one of the nice things about it is that it takes less memory, right? Because normally a triangle is 3 points, right? Every point has an x, y, and z coordinate. So you're talking every triangle would be 9 numbers. Here, though, if I've got this triangle 0, 1, 2, and I'm adding a new triangle 3, because it shares points 1 and 2, in order to store the second triangle here, I only need 3 numbers instead of 9. And then to hold 4, I need 3 numbers instead of 9. And this one, 3 numbers instead of 9. So for a really long triangle strip, it's 3 times smaller, essentially, in size, because it shares vertices. And so the triangle fan has the same thing, except the one point is always shared, and then there's quad strips. So you can build a model out of quads if you want, like that. The thing about a triangle, though, the reason why we use triangles is because anything can be approximated by a triangle, right? That's one of those classic mathematical theorems that you know, any shape given an infinite number of triangles, you can approximate any shape using triangles, right? And so it's just a purely matter of accuracy versus size, the number of triangles you have. And so you'll usually see triangles used for that reason, and it's kind of a common thing. Yeah, I don't know if there's any benefits to using these. I know some rendering engines use them for some reason, but I'm not sure why they would do that. Triangles are kind of the thing, and usually they have something called a vertex pool. So there's typically some array that holds all of the different points in your mesh, and then there's another thing that says where they're connected, and these are all like held in memory. Can you ever tell the difference between art generated by different polygon strips versus fans? No. It's highly unlikely you'd be able to tell the difference. It's kind of a low-level implementation detail. Yeah, when you're maybe modeling something, maybe, but yeah, I've never seen it really matter. Yeah, good question. Okay. So, how to make human skin? Yeah. Now you're all on the FBI's watch list. Okay. All right. So slide off me. Okay. So we are going to. So that was some lecture. I haven't lectured in a while, so thanks for putting up with that. So let me pop back into Unreal Engine here, and so now maybe some of this lighting stuff we've been doing makes a little more sense. You can see there's a shadow cast here. Here's my little Stonehenge thing I put up here, and so what's happening is the game. There's a sun up there. You can see there's a little bit of bloom on it. Right there, there's a little glow around it. What it's doing is that it takes the outline of this object here, and it projects a shadow volume down here, and everywhere the shadow touches, it darkens. Right, it doesn't get lit. And the mountain side does the same thing. This light bulb here is probably casting a shadow back here, but it's already dark, so you can't see it. Okay. And I got our cool little meadow here. Let's see if I can. Yeah, because I set the culling distance to 50,000. You can see it's actually getting a little thinner on the ground back there, but yeah, you can still see it. Like there's no noticeable popping. Whereas before, I showed that to you guys before? Like there's just a line in the grass, and it just appears as you get closer to it. And so as you come in, if you stare at it really closely, you might see some new plants appearing or something, but it's really kind of hard to tell. And then as I get closer and further away from the rock here, it's going to be swapping out level of details on it, like you can see back here, right? See that? So that's the 50,000. Do you see that? Do you see that line? The grass appearing? And so as long as you're not going to be, allowing the players to kind of, yeah, there you go. Bloop, 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 bloop. Yeah, that's a very jarring pop. But as long as you're not allowing the players to do that, it should be fine. And so all these objects here, as I zoom out, look at that bush here. It's not drawing the flowers on them anymore. See that? There's one flower on it. And then the more flowers appear. So that's level of detail. See that? Okay. Does that make sense to you guys? The level of detail stuff? The landscape handles it really transparently. Like you're probably not going to see any popping on the landscape. Like here's the outline of this mountain here. As I zoom back, yeah, I'm not seeing any problems with that. Okay, and there's a little light shaft down here. See the light shafts? Okay. If you were to zoom into the bush with a scope, would it show the flowers? Good question. It depends how you do the scope, right? So if you simulate it by like moving the camera closer to it, then yeah, it'll pop in, because the level of detail is based on your camera, right? Wherever your camera is.
How do you turn the?
Do you like the flowers I put in there, Rob?
The shadowing is terrible.
The shadowing's terrible. Thanks.
It looks Yeah, but I do like the flowers. What happened to my floating? What happened to my beautiful?
That was last semester. I started a new map for this semester. You can build something in this one too if you want. Show off to the students. Not right now though. Why doesn't the mountain cast shadows on the grass? There's an option for that I probably don't have turned on right.
How come I can't put a grass right there?
You want to put grass on the ground?
Yeah, it's
Here.
all rocky and terrible.
It's all rocky and terrible. Oh, how about we do this? Yeah,
Looks like we're floating.
yeah, we are because it'll put everything up off the ground. Starter content, materials, grass. But it's all. See how zoomed out it is. Kind of looks bad.
That's fine. Just a little grass.
So if we want it, we should. If you want it to just be on the ground, we can just put it on the ground and we'll redo the lighting. Okay, so what we're going to do today in Unreal Engine is we are going to talk about beginning programming. It's building lighting. Don't mess with it. Ada, don't mess with it. It's redoing the lighting.
Okay.
So we're gonna get into programming today, and I do have a lecture on this, but the general way that you interact with the world is a couple different ways. You can touch something, like if you come up and headbutt them.
Sorry.
You can come up and headbutt them. And
I'm sorry.
yeah, you're all right, girl.
Is
Building
that a termite
lighting
mound?
build is completed.
Is that a termite mound?
It's just a rock. There we go.
Ah, so beautiful.
And so there, this looks a little nicer now.
Can I build a house?
Not right now. I've only got like 30 minutes left in class.
Okay.
Both mapping and LOD use the same idea of showing less intensive stuff at further distances. Correct. Mapping is about textures, and LOD is about polygons. Correct. Yeah, that's the difference. It's the same concept. You don't want to waste a million. Like, let's say this rock here was 1,000,000 triangles, and if you had one a kilometer away, you don't want to spend 1,000,000 triangles drawing something that's going to take up 2 pixels on your screen. You know what I mean? So the further something is away, you can't even see the details on it. So don't waste your time drawing it, because every triangle you draw has a cost, right? You have to go through and rasterize it, which means you're grabbing the texture data. You have to light it. You put it into your Z buffer, and things can overdraw it and things like that for every triangle. And so you want to cut down on the number of triangles. And a lot of game development is really just about, when it comes to game engines, is trying to minimize the number of triangles you have to draw on the screen.
Where did you get the mushrooms?
I got it from a nature pack. And so, like right now, the game engine knows I'm up here looking down at the ground. My camera is facing this way, so that landscape behind me cannot be drawn, and it won't draw any of those triangles on the screen. So that's called view frustum culling. It knows what the camera is looking at, and everything that's not on the screen doesn't get drawn. And things that are far away, they draw less triangles. And if something's in front of another something, like if I put an object behind that cliff over there, I could probably figure out that thing's not visible either, and I don't even bother drawing it at all. And that's what a huge amount of like game engine development time, or the benefit of a game engine, or like what people spend time on a game engine on, is like trying to cut down as much as possible, because these worlds can be huge, right? You can have millions or billions of triangles in the world, of which only 1,000 are visible.
That's actually
What you doing, girl?
Oh.
Flew through the ground, girl. And so the game engines, I should say, in general, are really well designed. Well, assuming it's a good game engine, right? They're optimized to try to cut down the number of triangles on the screen as possible. What would it mean to draw something that wasn't on the screen? Well, if I tried drawing a triangle behind me, what it's going to do? It's going to go through every pixel of the every point on the triangle and try drawing it on the screen, and it's going to get a negative Z distance, and so it won't draw. But you're still going to go through every point on the triangle, and it'll try drawing to the buffer. There's a 2D array that basically holds all the color data, and then there's also something called a Z buffer that holds how far away those colors are. So for example, you have that golden box there, right? That's being drawn. And so after it goes through the process, every point on that box, it's going to look up the texture using that material thing that we've talked about. It's going to look up how much lighting it has based on all the different lights. And then it's going to say, all right, draw that kind of orange pixel at that point on the screen. And it is currently, what is it, about, I don't know, 10 meters away or something like that. And then it's going to try rendering the flowers behind it. And so those flowers, it's going to go through and say, okay, it's going to be green, it's this much lit, and it does all the calculations. All right, draw it on the screen at that same pixel location, but further away. And because there's something closer to it, it gets occluded. And so all the grass behind that golden box there, they're still getting drawn.
How do you copy
but
this?
But when it rasterizes it, when it puts it into the Z buffer, if there's anything closer to it, the closer thing gets drawn. The golden box gets drawn, not the grass behind the golden box. And if you try drawing something behind the camera, then it has a positive Z value, and so it doesn't get drawn at all because it's behind you. But you're still going through all those computations and things like that. And sometimes you do that because, like, if you have a mirror, right? If you have a mirror, then you need to render stuff behind you. And so they'll do, various rendering techniques where they will render things off screen for reflections and things like that as well. And so later, can you explain what Unreal Engine really does with triangles? You want us to remind you? Yeah, that's what I was talking about, really. The hello? Hey. Yeah, what's up?
I have to leave.
Okay.
So I'm going to lock the handle.
Okay.
And then when you leave, if I'm not back or Tion's not back, just
Okay.
lock the door handle.
Got it.
Okay, thank you.
Okay, sure, Robert. Thank you. So, so what the whole Unreal 5 thing is that it streams triangles in, right? So rather than having this LOD, this LOD, this LOD, this LOD, as you get closer, it'll dynamically go from 700 triangles to 710, 750, 800 as you walk closer, and as you walk away, it will dynamically reduce the triangle count. Because handling that kind of stuff is kind of a pain. And in your art, like, there are tools that generate the LODs automatically, but if they don't work right, and especially if they cause a noticeable pop, then your art team has to go in and manually tweak, okay, the third LOD has a pop on it, and they have to come in there and clean it out. So that's annoying. Okay. All right. So like in Horizon Zero Dawn, only loads the game when you look at it. that's another technique, right? Where like textures only get loaded when they're used, and so that makes loading a level faster. But the trouble is, if you ever like,
Deb?
I think you fell through the world, girl. And so like the first time, like you turn around, if you haven't loaded the texture for the door yet, then there's going to be hesitation. The game will hiccup because it has to sit there and load from disk the texture for the door. Now, if you've got a for the door, there's the door. If you've got a fast SSD, maybe you can load it fast enough, maybe in time to catch the next frame. If not, you're going to start skipping frames, and your frame rate will go bloop like that. And if you've ever seen like benchmarks for video games, a lot of times they talk about the minimum frames per second because that's when the game hiccups. Like you go whoop like that, and then the game's like, I wasn't ready for it. And it has to hurriedly load these textures, and the game goes, and you watch your frame rate, it goes like that when it does the load. And so another big thing that in game development, and the engines can help with this, but it's still something that game developers spend a lot of time doing, is figuring out when to load textures, right? So like let's say your graphics card can only hold 2 gigs of texture memory, right? If you try loading everything in the level and it's more than 2 gigs, you can't load everything in the level. So you have to pick, what am I going to load, what am I not going to load? And so what they'll do sometimes is they'll just be like, all right, this half of the map over here, don't use any of these textures. And this half, don't use those textures. And then you can get the budget in under 2 gigs or whatever target you're shooting for. And that's especially common if you're hitting consoles, right? Because consoles traditionally have had very little VRAM, very little video RAM. And then what they'll do is they'll put a doorway between the two areas, right? And so when you are going to go to the other part of the area, there's going to be a doorway there, and you hit a lever, and then there's going to be this long, intricate animation sequence where the lever goes down and these gears start turning, and you hear a rumbling sound, and the door starts shaking. What it's doing in the meantime is that it's loading all of the textures for the other area. And then the door slowly creeps up, and then you walk through and you don't see a loading screen. But there's a loading screen, you just didn't see it. And what it's Mass Effect, the elevators in Mass Effect. Does that make sense, Avina? Like, if you do you understand, like, graphics cards on a computer, they have a limited amount of RAM, right? And so all of these pictures, these are all pictures, right? Like the bricks and things like that. You turn the camera speed down. Click on the 6 there.
It's really
Click on the
hard
6.
to
Yeah,
do this stuff.
turn the speed down to 4. There you go. Yeah, then it'll be easier for you. So you see how, like, that's a picture of oak and stuff like that? All of those things have to be loaded into RAMs so they can be drawn. All the noise patterns, all of those things have to be loaded into RAM. And so what they'll do is, especially in consoles where you don't have a lot of VRAM, is that they'll mandate this half of the map can use these textures, this half can use these textures to get it under that 2 gig limit or whatever your target is. Then they have a loading screen, right? So when you transition from one level to another, what happens is that it unloads the textures you're not going to be using.
Dad, I think this one's upside down, actually.
It is upside down. It's a ceiling light. And so when you go through a loading screen, what it's doing is it's discarding from memory all of the textures you don't need anymore. Hey, we left area A. I don't need those textures. I'm going to area B. I need those textures. And it'll sit there, and you'll hear the hard drive spinning, right? What it's mostly doing is it's loading textures off disk, so that when you walk in and you see a door, it already has the texture for the door in memory, and it can draw it. If you don't do that, then the first time you look at an object and there's a texture on it, you don't have it in your graphics card memory, it's got to spin the disk,
How do you
and
copy?
your frame rate goes like that.
How do you go copy?
How do you copy it? Control W. Okay. You're confused how Unreal Engine gets around triangle count, especially if you have to worry about it, because they made a
What
lot
just happened?
of advertising for putting in big statues
Yeah.
of millions of triangles.
Oh.
It just duplicated it. So move it around. Yeah. So what Unreal Engine 5 is based on having a high-speed SSD. So rather than having to load it in advance, because especially when you have a hard drive and you hear it spinning and things like that, spinning disk hard drives are, like, not fast, and so you have to preload it in order for the game to run with any sort of performance. Unreal Engine 5 is based on the notion that there is going to be very, very high-speed SSDs, and in fact, in the PlayStation 5,
It's not
and
copying.
it did. Here, let me
It's
show you.
just in the same place.
Yeah, it's in the same place. So move it. Yeah, see. So you got a couple of them there now, and so Avina, the notion is rather than having to preload everything, you just leave it on disk, and SSDs are fast enough now that as you get closer to it, you hold the texture data, or you hold the triangle data in such a way that the most important data is first and the least important is last, and as you walk closer, you just kind of progressively load things as you move towards them. And if it's fast enough, if your SSD is fast enough, then it's seamless. And so the Epic people actually pushed the Sony PlayStation developers and the Microsoft Xbox developers to actually put in a very high-speed SSD into the latest generation, because they're like, hey, this is our thing, you guys need to support it, and so they did. And so both the PlayStation and the Xbox actually have very, very fast SSDs now, which is a game changer, because if any of you guys ever played, like, Xbox 360 games, like, man, the loading times on those things were terrible, like
What?
the loading time for, like, Skyrim, like, or like you would landscapes. No, don't. You copied the entire landscape, girl. Hit no. Don't copy the landscape, please.
An island.
Yeah, but yeah, I think that if you want to be a gaming PC person, like, you're going to need to get an SSD, like a high-speed SSD, to run the upcoming Unreal Engine 5 games. Yeah. The good news is, like, a small SSD is actually fairly cheap these days. The big ones are still super pricey. The 8 terabyte SSD I just bought, it was like $1,000. Yeah, which is why I teach summer school. I teach summer school to upgrade my gaming PC mostly. Okay, time for me to lecture, girl. I got 20 minutes left. Okay, thank you. so let's talk about programming in a game. All right, so at this point it might be cheaper to do pre-built. Yeah, the components industry is still pretty terrible. Okay, so how do you interact with things in a world? Like if you're a player, you got here flying right through it. So these things I can shoot. This rock here, though, when I click on it, you see the balls go right through it. Okay. So that seems a little weird, right? And then this thing is just, this thing's floating in space. This one moves. This thing's floating in space, right? Looks a little weird, right? It's a little weird. Penguins immune to bullets. The bushes.
What if you take physics off of the head?
If I turn physics on the head, then it will topple over. So you see how everything's floating in space? It's because I deleted the floor for my daughter who didn't like the floor. But you know the landscape looks nice now. So probably offline, I'll probably move everything down and go through that. So how do we interact with things? So first of all, you can do collision. So touching something is one of the three primary ways that we interact with the world in a video game. And so here I am creating a ball, and the ball is touching something, and then it does something. In this case, it's imparting a little bit of momentum to it. Okay. Here I'm touching this, and nothing happens. I can make something happen, but nothing's happening. Here I can walk through it. So this thing has collision turned off. This is collision turned on.
How about that?
This has physics turned off. These have physics turned on.
How about that one?
That one I can walk through as well. And look, see how I can see out of it? Do you guys see this?
Wait, isn't that what you do for a custom team fortress? Like you're allowed to walk into it, but the people can't see you.
Yeah, in the hunted map. Very good, girl. So this is something called backface culling. So remember how I said like a big part of like what a game engine does is to reduce the number of triangles being drawn. By default, a triangle only draws one side, the outside. The inside does not get drawn. And the reason why we do that is because we got all these triangles here on the backside of the rock, and by default you can't see them, right? If you have any sort of closed surface like this, you can't ever see the inside of it, right? I'm not really supposed to be able to walk through this rock. You know what I mean? And so this is an optimization technique. So you can see that these triangles are just not getting drawn until I come through the backside, right? This is something called backface culling, and every game engine that I'm aware of does it, okay, as an optimization technique. So that gets rid of half the triangles in the rock, right? It just looks at the triangle, and it can tell if it's facing us or not facing us based on if the triangle is, if the points are clockwise or if the points are counterclockwise. So if the points are one or the other, it's arbitrary which one you pick. Then it's facing us and it draws it. If it's counterclockwise, let's say, or it doesn't matter, it's arbitrary, then it doesn't draw it. And so that gets rid of half the triangles. Right? Kind of cool, huh? Okay, so how do we make something happen if we touch something or if we overlap something? Okay, like what if I wanted to make it so that every time I touched the texture sample thing here,
it explodes.
It explodes. Okay, all right, that wasn't where I was going, but all right. Do you guys want to see it explode when I touch it? Is that? My mouse is shaking for my daughter, shaking her head. Ada, you're laughing. Is why not? Okay. Okay. I'm just going to drop these things to the ground. So.
How do you drop them to the ground?
Press end. You select it. Press the end key.
Well, can you put those to the?
Later. We don't have too much time. Okay. Mm-hmm. So you want to? My daughter has requested when I touch the texture sample panel here, it will explode. So I feel like it probably should have like a I don't know, like a dangerous texture on it or something, you know, to make it more look like
that one.
This one. Pretty good. There you go. So when I touch this, it's gonna explode.
Or how about glass? Glass. No. Everything is glass.
Like that?
Yeah.
And so when we touch it, it's gonna shatter. Okay. All right. That makes sense. Okay. So here we go. This is the key. This is the key thing for today. Everything I've told you about, there's no midterm or final in this class, so it's just for your own personal edification. But like when I started working in the games industry, like my boss explained to me, this is what backface culling is. This is why, this is why when you walk inside of an object, you can look out of it. Like this is the kind of stuff that people explained to me when I started working in the industry, and I'm explaining it to you. So hopefully it was at least interesting for you guys. It won't be on the test. You can forget it, but I wouldn't. It's all useful stuff. Okay, so here we go. The key takeaway point today is blueprint. Add script. So we are going to add a script. We're going to add programming to this glassy texture sample object. Although I still think it should look like a bomb or something.
Did you sign them their yesterday's homework?
Yes, I signed them yesterday's homework. I kind of want to make something that looks like a bomb. I don't know. Okay, fine. We'll do glass. Whatever. It's fine. Okay, so I'm going to, with this thing selected, I'm going to choose blueprint add script. And it's going to be like, what blueprint name do you want? And I'm going to give it a name of like shattering glass, because that's what was requested. And I'm going to put it into my build directory.
Dad, look.
Yes, they said yes, sure. So I'm going to put it into my build directory here, just so that all my stuff is in one place. So again, I selected the texture sample object there. And with it selected, I chose to add a script to it. So I'm going to make it smart. I'm going to make it intelligent. Not too intelligent. I don't want it taking my job.
Walking around.
Yeah, probably not. But I could. But yeah, we'll just leave the rest of it here. And I hit select. And what you will see is a zoomed in view of the object that we're turning into a blueprint. Okay, looks cool. And over here is the thing. So do you guys all see this tab called Event Graph? So go ahead and click on that. So once you've chosen to add a script to your object, this is where the magic happens. This is where it becomes intelligent. Okay, this is where you write the program. Okay, you guys all see this? Thumbs up. Click on an object you want to make intelligent. Click on Add Script, and then go to the Event Graph.
I recommend not making it have legs and start walking around.
No legs. Okay. So what we want to do is what? When we touch it, it shatters.
Or maybe if you shoot it, it shatters.
Shoot it. The balls actually, it's a little weird with the balls because the balls actually don't spawn events. But yeah, we can do when the player touches it easier. Can be damaged. We might probably do that. Collision. So collision here, generate overlap events. We might need to go back over to here. Let's see here, simulate physics. No, here we go. Okay, so sorry, before we get to the event graph, we need to enable collision on it. Okay, so go back to the viewport here, and on the right hand side on the details tab, you will see that there is a section called collision, and the important thing to do here is to turn on simulation generates hit events. So when you walk into it, it will generate a hit event. So that is what's going to trigger our code to cause it to shatter. Okay. So once again, click on the viewport and choose simulation generates hit events, and everything else should be fine. I think. Let me look at it. Collision presets. Default should work. We might come back and play with this. There's a lot of options. Okay. So yeah. Okay. So did you guys all get this? This thing needs to be checked here. That's what's going to make it so that when you touch it, it's going to fire an event called somebody ran into me. You're lagging behind a bit. Okay, so Avina, step 1, click on some object you want to make intelligent. Step 2, click on the blue blueprints button. And then step 3, from the viewport tab here, come over to collision and choose simulation generates hit events. Okay. So tick that. You got it, Avina? Okay. All right, so You can see that there's some events here already. We are not going to use these for now, so I'm just going to select them and delete them. You'll notice that these things look pretty much like what we've been working with the materials editor. And what we're going to do is we're going to right click and we're going to add a new event called event hit. So my neck still hurts from her headbutted me. Yeah, you're okay, B. It's good to have a tough daughter. Okay, so from the event graph, right click, type in event hit. Spaces don't matter. If I put a space in, yeah, it doesn't really matter. It'll still show up. So event hit, and then we'll get this. And so what will happen is when we, the player, walk into the object, whichever object you guys picked, then it will do something. And this little white pen here is the flow of execution. So you have to drag out from here, and whatever you have connected to event hit will run when we touch it. And so the simplest thing ever, and this is how I always start with my things, just to make sure that, like, because sometimes I'll forget to tick a checkbox or something. The simplest thing ever is just to print something. So I dragged out from here, and I'm going to type print, and I'm going to print a string to the screen, and I'm just going to print out, yeah, hello. That's fine. Okay. So here is my hugely complicated intelligent program. So when something hits the object, it will print to the screen, hello. This is coding. It's visual coding. Yeah, in IS-58, I don't do any text-based coding, except maybe in the mod section. We'll get to that later. For now, we're going to be doing all block coding. That's what it's called, visual coding. Okay, it's still a program. It still basically does the same thing. It's just you don't need to look up tons of documentation. You can just drag out from something and type a little smart search, and it's actually much faster to code simple things here. Yeah, syntax, semicolons, none of that stuff. When you pull out from here, for example, it only shows you things that will take one of these things. When you pull out from here, it only, if I type break, it'll only show me the things that will work with these yellow things here. So it's actually a fairly fast way of getting into programming. Okay. Okay, so that's our program. We're going to hit compile. To compile the program, hit save it, and then when we play our game, you can walk over here, and when I touch it, do you see how it says hello on the screen there? So print is usually used for debugging stuff, but I pretty much always start with it just to make sure that everything's kind of set up right. Like if I had forgotten to tick that box for it to generate collision events, when I walked up to it and touched it, nothing would happen. And that's the worst thing in Unreal Engine, and it's an ongoing and the worst thing in Unreal Engine is when you get all this stuff set up and nothing happens. Nothing happens. Like you click and just nothing happens, and then you just don't know. You just don't know, right? Like why did nothing happen? Is the event not firing? Did I not bind the mouse click to the event, and you just start going like, why is nothing happening? And to make things simple, that's why I always start with just printing something, because there's no if statements in here. There's no complexity. If an event hit happens, it prints hello to the screen. Done. Easy. Okay. It didn't work for you. I thought I set check marks. Did you remember to compile it and save it? You have to compile it and save it, or it will not fire. And so under the viewport, with the thing selected, make sure that your collision has simulate generate hit events on. And so it's basically a black box with Unreal. It's one of the more annoying things, because when you're doing regular programming, you can kind of put printout statements everywhere in your code and kind of follow along with what's happening. With Unreal, if it doesn't generate the event, it doesn't generate the event. And so Avena right now, he has simulation generates hit events turned on. His event graph, he has event hit hooked up to print string, presumably. He hit compile, he hit save, and then when he goes into hit play over here, by the way, you have to hit play. If you don't hit play, if you're just in the editor, nothing happens. Right? You have to hit play, and that actually runs the game. Then when you touch it, it does hello. Yeah. Yours only says hello 2 times. Well, I mean, if I stop moving, right? But if I walk into it again, every frame. Okay. Yeah. So Avina, go ahead and post a screenshot of what you have, and we'll take a look at it. All right. So we want it to. Let's see what we got here. Event hit, print string. I can't really see that. Event hit, hooked up to print string. Hit detected, print to screen, print to log, text color duration 2. Okay. Class shatter. It's not saved. So remember to save it. Yeah, should be fine. Okay. Collision event generates hitbox. Yeah. Okay. Yeah. Remember to hit save, and then go into the world. And one thing you can do to help debug it is you can do a split screen setup like this, and you can actually watch the blueprint. So if I come over here and hit play, watch what happens when I come up and touch it. You can actually see it fire. You see that? So you can. It's really neat. Like it's like blueprint's really cool. And so when you walk up and touch it, you see the like bloop and bloop, and so you can see if it's firing or not. Okay. So that will tell you if it's a problem with your print string or if it's a problem with the event not firing. Collision presets default. Simulation generates hit events. Nothing happens. All right, I'll have to. I'll have to help you after class. So we want it to shatter and end. Is it not because I messed stuff before? It's possible that the overall object itself has collision events turned off. There's that's the annoying thing about Unreal Engine is that when nothing happens, it's just like why, and so yeah, you just try making from scratch, like put a box on the ground and just like put a box on the ground and on the box, go to collision, make sure the box has simulation generates hit events on, add a blueprint to it, go through that process again. Because sometimes, like when you're editing an object, there's the root part and then there's the child part, and all of them have to have generate collision events turned on, or it won't work. But I'll work with you after class. So for now, I'm just going to delete the print string because I know it works, and I'm going to come in here and I'm going to do 2 things. So maybe 3 things. Maybe first I'll do a particle effect, like I want to make like a braking effect or something like that. So I can type in particle. Let's see. Spawn emitter at location. That sounds pretty good. So this is the particle effect system. So you can make it that where you touch it, it'll do a little explosion or something like that. There's only a few particle effects that come with this starter kit. Again, this is something where you'd want to download more assets for it, like get a glass shatter effect if you want to do that. I'm just going to do like explosion because that's the closest thing I can think of. And so where is the explosion going to take place? Well, at the place where we hit it. And that is right here. So you see here where it says hit location? So I'm going to drag from hit location into the location where the explosion is. It works with the box. Yeah, it might be because the parent of your texture sample object doesn't have collision events turned on. And yay, that's the fun part of Unreal Engine, is that there's a lot of things where things can hide and just cause nothing to happen. So so did you guys all see this? I dragged from hit location here into location here. A yellow pin is a vector. It's usually like an XYZ. So hit location will be set to the place where probably my face touches the object, and then that is the place where the emitter is going to be spawned. If you don't hook that up, it's going to spawn at 000, which is the world origin, which is actually probably nearby. I think the world origin is actually right next to there. But it'll look really weird where you break something and an explosion happens over there somewhere. You know? So auto destroy turns itself off after it's done running. Yeah, that looks good. Okay. Then I'd like to play a sound, so I'm just going to search for play sound. And this just, you just do this by right clicking, or you can drag out from the white pin. So what happens is that the event happens right here. Then it spawns the emitter. Then whatever I drag out from here happens next. And so I'll just search for play sound. And so I will play a sound at the same location. So I'm going to hook up the hit location. Again, that's the place where contact was made. And what sound am I going to play? I'm going to play the explosion sound. Why not? Do I have breaking glass? Do I have a breaking glass sound? No. I'm just going to go with an explosion. It's simple. Okay. And then I am going to remove myself. Okay. So this is my entire event graph. This is a program. Okay. And this is an event-driven program. That's why it's called an event graph. This thing doesn't run. It's not like running constantly. This is a very different model from how most people are used to programming. Usually when you program in like CSI 40 or CSI 41, you write a program and it starts here and it goes line by line and it's running. This is a different model. It's a different way of thinking about it. You're writing a program that only runs when something touches the object. So this thing will not consume any CPU time. It won't consume any resources except for the very small amount of RAM used to store it. But when the player walks up and touches it, then it runs the program. And it will spawn an emitter, it'll play a sound, and then it blows itself up. Okay? So we can do compile, save. Always remember compile and save. Those are your friends. You're going to be doing those a lot. And if you don't do them, nothing will happen. Then I will hit play. And let's turn up the volume on this to max. This will be fun. See that? So when you walk up and touch it, blows up. And can't do it again now. One thing that probably should be fixed on this is that while you have it set, don't have it be static. Deleting a static object is a no-no, right? So what we're doing right now is sort of violating a promise we made to Unreal, because we told Unreal this thing will not go away. We set it to static. When you set something static, it cannot be changed. Cannot be changed in the game.
I didn't see it explode.
And because it's static, it has baked the lighting into the world. So even after we delete it, like this, the shadow's still there. You see that little outline there? So
It's a ghost.
we need to set this to movable, or it can be changed but not moved. Yeah, let's do stationary. It's not going to move. And then we can rebuild the lighting. Where are you? Build lighting only. And now when the thing gets blown up, the shadow will go away, hopefully. Okay. So the lighting does not update for static instances. No, because static things are not supposed to change. Like what we did there was like, you're not supposed to do that. When you have an object labeled as static, it will never move, it will never change, it is fixed, it is static. And so, like walls and things like that are oftentimes marked as static. Map check found some issues, really. Wall, oh yeah, Ada cloned a bunch of things. So it's complaining that there's a bunch of things at the same location.
Can I see?
These walls over here,
Yeah, let's...
you made a bunch of duplicates of them. That's fine. But you see how the shadow updated a little bit? And then if I hit play, over here, you see how there's a shadow kind of,
Can we make it have shadows of black?
and the shadow's gone. Okay. Yeah, we'd have to get like a particle effect pack or something like that to
Do that.
do that. Yeah. Okay. Whoa!
What?
I changed the field of view. That's a Z and C while you have the thing held down. Okay. And then these guys are still up in the air, huh? No, they're not. Weird. The shadows are not working right. Okay. You can be on the ground, and you can be on top of you, and you. Okay. All right. So that is it for today. So once again, your homework is to do what we did in class yesterday with the landscaping. So adding layers, paint a road on it, and then automatically generate grass. That's your homework for tomorrow. We're going to work on this again tomorrow. I'm going to be driving back to Fresno tonight, and I'll be back in my usual setup, not a real estate office or whatever this place is. What was the name of the event hit again? It is called Event Hit. Yeah. And so, yeah, like if a parent is set to not generate events and the child is set to generate events, then it won't generate event. Like it's kind of irritating, you know, and it silently does nothing. Like it doesn't warn you about it or anything. I'm done with my first class, and then the second class we will do now. Okay. Did you get your worksheets done and stuff? Get your worksheets. Go. You've been sitting here this whole time playing video games.
I did bring the Nintendo Switch.
You did bring the Nintendo Switch.
No,
That is
I
also.
No, I didn't.
You did not bring the Nintendo Switch. That is also not doing worksheets. So do a couple worksheets. I got one more class. Okay. All right. Doesn't seem to be showing up. So from your script, from your event graph, right click and type in event hit. I deleted all the other events out there. There's events for like when it's created. Every frame you can do something if you want. There's events for on overlap if it's something that you can enter, like that rock that I have over there. I could create an on overlap event. Let's say when somebody enters the rock, you know, darken the screen or something like that. Okay. Screenshot, please. Yes. All right. No, I posted it already. Yeah. Oh, you're in the construction script. Yeah. Cool. All right. So that is it for today. And I will continue with the IS-50B people in a second. All right. See ya. Hit a wave. Goodbye to everyone.
Goodbye.